Our next presenter is going to be Shailendra Tripathi from Tegile, and he's going to talk about improvements to the L2ARC. So please welcome Shailendra.
Hi, I'm Shailendra Tripathi. I lead the file system team in Tegile. Just to give a context, roughly around November 2013, we took the GFS from the Illumis, and since then we have been developing the GFS features independently. For various reasons, I'm going to talk about them, why we had to do our own development, mainly because of the things we were doing. They were mainly on IOPS or latency side. And some of the problems which we were facing probably were not even discussed at the time in OpenZFS community. I'm just going to talk about briefly current model. Before we did this project, what was the problem, what are the challenges in that, and how did we went ahead and improve the IOPS and bandwidth, which we saw on that. So just giving a brief, how does storage pool allocator is bundled in current GFS. You can plug in any device under several meta-slab classes, log class, L2ARC class, or data class. When we started, Tegile added another class for meta class, and especially putting all the metadata on the faster media SSDs so that we can put things like all the indirect blocks, dedupe indexing tables and all that on a meta class. So it has been a peer to the, I'll say, log class and data class in that sense. It gave good improvements in some of the cases, but still, I'll talk about the problems which it has. The problem was the resource utilization. You have few number of drives. How do you utilize the drives in such a way that it's very efficient? So the model is that you put some devices to the log devices, or some to the cache, or some to the metadata devices. So they are either statically partitioned, or you create regular partitions and put them inside that. So two approaches. Dedicated devices, we realized very quickly it's not going to work because we want to share the SSD devices, which are more performant, latency-wise and all that, among several data classes, not only in few and definitely not in dedicated manner. So why not to do partitions? The problem with partition is very inflexible. Once you have created the sizes, you cannot change the sizes before doing something bigger to the pool and all that. And even bigger problem, what do you do on the partitions when two class of data are writing or pounding at the same time on the same device, and there's no mechanism to throttle, say log class is pumping? How do I ensure the meta class or cache class is not completely starved? Because underlying they are talking to the same device, and there's no mechanism to make them pipeline in a nice fashion. So what can we do? So we came up with an idea, why not share all the devices and make it completely virtualized and implement all the services, all the classes on top of it. What it provides is it gives you shared capacity. You get IOPS and bandwidth completely shared. And also, because we are talking about log, cache, meta, all of them have different data protection requirements. For example, cache, I don't need to worry about drive failure and all that. I can just probably discard it whenever there's a problem, but I must provide a very good data protection for meta or log whenever I'm doing that. Secondly, there is a very, very different characteristic in the applications. For example, log is completely sequential. You're just writing big logs and everything, but metadata is completely random, IOPS bound. So essentially, in any file system users, you will always see there's a bimodal pattern of the user, either in throughput or in the IOPS. And by sharing these devices, we can utilize both parts, throughput and IOPS, in very, very efficient manner. However, we also need to provide some of the quality of service, because the moment you start sharing, you need to also make sure some of the services don't get starved, or at least you have some mechanism by which you can provide services getting something for each class of service on top of it. Just whatever I talked about the services, so comparing with the slices are partitioned, when you have everything in partition, you're just bombarding the IOs to the device directly. There's no mechanism that you can control. But when we have shared all these classes on top, we can funnel through a separate priority queue, and you can put dynamic or adaptive weights and process them as per your need. So how does iFlash pool look like? So just flip the devices instead of vertical, horizontal, and I'm showing how a logical view appears. The storage is still divided in meta-slab classes. We have different sizes, like fixed 4 gig sizes of slab instead of having 200 fixed per drive, but pretty much similar concept. And then pull it, all these classes on top of it. So you'll notice log class and meta class, they appear exactly same, but L2ARC doesn't appear, which is maintaining whatever is the current GFS model, where L2ARC is not necessarily a separate meta class in true allocation sense. We maintained it exactly same for 2 reasons. We wanted to have extremely fast allocation performance. If we go to any other allocation structure model, it basically means you have to pay some price for allocating in the L2 cache, and we want it extremely fast. So it's just a rolling cache model, your rolling log model, you keep writing sequentially. So allocation is almost always some atomic instruction. You don't need to worry about all that cost of the allocation, no space map involved and all that. So it provides a pretty flexible model to allocate. And the way L2ARC is designed, I will talk about a little more in detail. It basically exploits underlying devices for both IOPS and bandwidth efficiently. In terms of implementation, we had to come up with separate items because we wanted to have different allocator. For example, we didn't want to have the same allocator for each class of service, so we made the changes so that allocator is per class. So every meta-slab class will have its own allocator, it will have its own priority queues, and also load of space map load and all, they also have a very different policy. For example, log class, we don't unload at all. We keep it all the time loaded. It provides very efficient mechanisms to condense, coalesce the smaller blocks, and we get the contiguous space by that way. And also every class has its own data protection type. So you can choose, you can configure, all of these are configurable with some default. So metadata, you can choose mirror, triple mirror, whatever, cache, no redundancy, log, mirror, or triple mirror, whatever you type. So how did we end up providing all this? Block pointer only supports 3 pointers. We didn't need to do anything. Only thing which we needed was that in the allocator, we strictly enforce the drive, that every allocation is aware of which drive it's coming from, and every block pointer, every allocation goes to a different drive. And that's how we implemented the mirror or triple mirror on top of it. Coming back to dynamic resource sharing, once we pull it, so we became more greedy. How do we efficiently utilize the capacity? For example, let me give an example. Let's say I dedicate some capacity to metadata. When I create a pool, definitely nobody is using that much metadata. So take an example, say out of 100 gigabyte of SSD, maybe 1 megabyte is used initially. So why do I give everything to metadata? Maybe I can just give 1 gigabyte and use remaining to the L2ARC or anybody else who is going to utilize it. And when there is a need that metadata grows, I can dynamically pull or take away the data from the cache and put it in the meta. So this is the crux of the USP here. Move the data from different classes to other class. In our practical use case, we have considered only cache, but there's nothing which restricts doing for others, although mechanism will be slightly different. So just given a hint, we have, as I said, we initially give some slabs to log and some slabs to meta, and cache almost takes everything. When there is a pressure on anything, log or meta, I have given example here in the meta, we can say, okay, I'm going to take away some space away from the cache and give it to meta. So there's a shrinker, dynamic shrinker algorithm, basically, which will figure it out, 4 gigabyte worth or 8 gigabyte, whatever is the slab size. and it will shrink the cache in that much and dynamically attach it to the meta. Now meta grows from 1 slab to 2 slabs, and it can use, or you can put it to the log. However, this required several enabler changes because straightforward we couldn't have done it, and there were other reasons why we had to do that. First change we had to do was that we had to make ARC and L2ARC independent. Right now, at least when we took the GFS, they were completely intertwined. Basically, L2ARC was visible in ARC, indexing was in ARC, there was no separate indexing for L2ARC. That created a problem for write bandwidth. So we separated it out, ARC and L2ARC. We had to pay a little price of separate indexing for the L2ARC, but at least it allows us to scale the bandwidth to the number of devices underneath. Second change we had to do because we wanted to make, we want to take the whole SSD space as a cache, so we need more indexing memory. And in the model which we had, it's roughly used like 160 to 170 bytes for one structure. It seemed pretty much very high. So we separated out L2ARC, made a very compact 64 byte in-core structure. It allowed to go more. Of course, indexing, if you have many more SSD devices, require some other persistence model, not only memory indexing. We can talk separately. So now, also we had to change on the way we store the L2ARC. It's completely persistent L2ARC and stored as a linked list of 1 megabyte pages. And that 1 megabyte page linked list chaining allows us to quickly scan from a given point to given point and take over the space. That gave us a very nice model that we can figure it out given an offset and given a size, where is that chain, and that chain I can plug it back to either log or meta as required. And I mean, just brief idea how it's linked. Basically, chunk has its own user class. Basically, chunk is the 1 megabyte page which I just talked about, and all these 1 megabyte pages, they have head and tail. As I said, we do not want to spend any time in allocation, so we always keep writing at the head and cleaning at the tail. And we have some mechanisms to retain L2ARC pages, which basically means we need to write back at the head if any of the L2ARC blocks are hot. We have separate mechanisms to track them, and we refeed them in the head so that they remain into L2ARC instead of getting thrown away. It's kind of a runtime recompaction of the space, but it also eliminates the need for maintaining any elaborate allocation structures. And the L2ARC hash table is very similar to buff hash indexing table, whatever is in for ARC, almost similar, just that it works on the L2ARC devices. And the L2ARC 1 megabyte buff page, basically it has all the headers. So when we need to bring back anything in the memory, we just scan the L2ARC buff page headers, and it basically constructs the hash table, and it's good to go at that point of time. Coming back to some of the performance, this performance comparison is with when you have partitions on the devices. The way you have partitions, basically you partition front part to log and remaining to meta and some part to cache, like that, and compared to iFlash. So orange bar is the one which is with iFlash because it is sharing. I'm showing 3 sample IO meter performance runs because they are kind of the worst cases for random performance. Mixed load of 50% random write, 50% random read, and RR0P is basically absolutely 100% random write. So as you can see, the same set of device, there's no change. 4 SSDs used in different model provide almost twice performance, and if you see latency also is significantly reduced because we have more bandwidth or IOPS available during the serving. So we did another test with a bigger block size. Let's see how much it improves if it is sequential kind of workload or slightly bigger block size. So even at that point, it significantly shows improvement in the overall performance as seen by the IO meter. And latency is even better here because at the higher block size, it's a bandwidth which is even a bigger problem. So sharing these devices provided even more boost in the bandwidth. So once we've had this idea of iFlash, say, sharing only on the SSD devices, if you think about it, if I just say log class is nothing but a streaming class, sequential streaming, and meta class is nothing but a random IOPS performance class, why can't I make the similar model for my all-flash pool also? So you can just assume this log class is nothing but a streaming class. What it gives me, two things. One, the allocations never spread across the disk. Because if you have anything which is you're writing temporarily and you're going to destroy very soon, there's no point writing in the whole drive, and we just contain to very small part. Another thing which you do is that we keep these log or streaming classes loaded all the time. That provides me two benefits. As it is freed, if you have unloaded space maps, you never have an idea where is the biggest contiguous chunks. But when you have a loaded, you can always find the biggest contiguous because the tree is already coalescing it in the runtime. Meta class, same thing as I said, you can have separate allocation mechanism. And I didn't talk about the allocator. Also in the log class, you can have completely separate allocator from the meta class because log class, you know that you're going to, allocation cost is the most critical factor. Everything else is secondary. So why not optimize it in such a way that you're completely writing at some sort of a head and just keep moving and then you roll back. So it still follows the MetaSlab class model, but it starts from say MetaSlab 0, 1, 2, 3, 4, 5 till the end and then comes back to MetaSlab 0. And if it is temporal class, most of the storage is, most of the used structures are freed, so it basically remains steady. For meta class, we have completely different policy because we want to optimize space efficiency and all that. So we try to pack as much as possible in a given MetaSlab class before we move to different class. So same idea, whatever we had on the iFlash, we incorporated into all-flash to provide different kind of quality of service performance for streaming and random I/O applications. Now you can think that you can put like logdb lens and log class and some other things on meta class on top of it. You need some other administered intervention to be able to do that, at least for now, but it provides a platform that we can provide that also at top level. In a sense, it provides very efficient resource sharing, creates multiple streams. It also provides a good advantage because it creates more parallelism at the SSD drives, which are very good. The more queue depth you have at the drive level, they perform even more. IOPS are even better. Adapts dynamically. The resource sharing is dynamic based upon size or threshold of, say, fragmentation. We can change, and it exploits the bimodal patterns found in almost every file system at various times. And GFS is pretty neatly bimodal. There's a data phase, and then you have metadata phase. So there's completely nicely aligned bimodal patterns, so you can exploit them. And aggregate performance is much better compared to dedicated one. It's very extensible. You can use it to all-flash or anything else if you want, and you can provide the extensible benefits to the application. Questions? Yeah.
So since you have an all-flash array, I was wondering what kind of advantages would you have from an L2ARC device?
We have both kind of arrays. The question is, since we have all-flash array, what kind of advantage you get with L2ARC? No, we have both kinds of arrays, hybrid arrays and all-flash arrays, and both of them are almost 50-50 use cases for us.
It sounds like, so the L2ARC eviction policy in the normal one is kind of horrible because it's just overwriting whatever was written longest ago. So it's just like round robining among the disk. And it sounds like you're still doing something like that, but you're also giving some benefit by like rewriting frequent stuff.
Correct.
I was
Right.
wondering if you could talk a little bit more about
Okay. So basically,
what's the practical effect of the changes that you've made?
right. So similar to ARC, the best thing about the ARC is that it provides you the resistance to sequential writes and all that kind of things. So we wanted to have something which, even though we moved to different models, how do we provide that kind of thing even at the L2ARC level? So we have basically something called a heat index for a block, and we maintain that heat index. And there's a pool-wide heat index maintained saying if anything is above that heat index, we are going to retain them. So essentially that provides a hit that if my block has been hit, say, X number of times, I'm going to retain it. So basically, instead of throwing it away, it feeds it back to the L2ARC again, and it still maintains the sequential nature.
So, you all said persistent, which means you reload it at boot or reboot. Is that done synchronously or is that done asynchronously?
No, it's all asynchronous. The question is, during boot time, do you load the L2ARC synchronously? No, we don't load anything synchronously. Everything is asynchronous, and it's per device. So as many number of devices, as many threads to load, but it's still in asynchronous.
How long does it take to load that?
Typically for 500 gigabyte drive, if it is all L2ARC, less than a minute, because we scan only the header part.
When's the last time you pulled from upstream and merged the code together?
So, as I said, the biggest pull which we did was in November 2013. After that, bug fixes which we see, generic bug fixes, we pull them in, but unfortunately it has diverged so much that we cannot do any pull at this point of time. Everything, a lot of good useful features we are not able to pull because there's a huge variance in our code. But some of the changes which are good, for example, compressed arc and all. So we are literally taking the idea there, and we have to, of course, re-implement because our arc is completely different than whatever is in the community. So we are taking the logical idea, and we have to do it, unfortunately, ourselves, that part, to exploit that feature. Yes.
So traditionally, the types of flash devices that you use, for example, for a log or L2ARC or even general purpose storage, are very different kind of types of devices in terms of endurance, write performance capacity, and kind of playing those trade-offs. So how often do you actually, for example, if you take like the traditional L2ARC device and then put a log device on it, do you find that you're going to start chewing through like endurance a lot more rapidly, or how do you see like the lifetime of devices changing when you start to find these different use cases?
Okay. So at this point of time, maybe 4 years back, we had some concern about the endurance, whether we have some endurance problem and all. But at this point of time, at least in last couple of years, we never see any problem related with endurance. And our log devices, I can tell you, must have seen at least several million times of iterations over that device, and in the field, like more than 5 years in field, but still there is no problem in those. So from the device perspective, though, we technically qualify the devices which we want to use. Mainly we have been using SanDisk and SGST devices for that purpose.
What do you do when, like, your metadata class is full and you still have space in the data class? How does the algorithm deal with that?
So right now, if it is a hybrid system, we used to have a model where if metadata class has a problem, we can spill it to data class. But if it is disk drive, it's a pathetic performance problem. So we have stopped doing that. Instead of that, we have addressed the problem, which is the metadata consumption. So biggest consumer for metadata in our use case is the DDT table. And we have added a mechanism where it will basically in background keep trimming the DDT beyond certain size. So we basically go ahead and find all the reference count 1 entries, and those entries we set 1/3 or 10%, whatever is the appropriate size at that point, and we keep trimming so that we never run out of the metadata. So workloads, basically two types of workload. The representation which I did is mainly the VMware kind of workload, which is absolutely brutal and random. There's almost no sequential workload. So if I go back here, I just put one sequential workload here. So these three are the complete representation of, say, VM and database. Both VM and database have almost similar profile. Very, very little sequential and mostly random. Just for the comparison purpose, what if our sequential, let's say everybody is writing sequential, what happens? I did that also. This basically means I'm just writing sequential in small size. So mainly it doesn't happen in small size, doesn't happen in many applications, but for 32K at least in database log learns or backup workloads, in some of the use cases we do see. So even there we don't see the impact. So this is, I'll say it's VM and database workload representation here. This one is 32K is basically SQL analytics or bigger block size databases, those kind of things. And in those use cases also, this is mainly with very highly dedupe enabled workloads. Basically, everybody is running with dedupe and all that.